everyone. My name is Rachel Hammond, and I am a molecule maker in the Burke lab. Now, as Marty mentioned, computers can use math to make predictions, especially predictions regarding the function of molecules. And today we will be discussing that in the context of K-nearest neighbor analysis, also known as KNN. As Marty mentioned, statistical models can be used to make predictions. Likely you are all familiar with the concept of linear regression, in which a set of linearly correlated data can be used to draw a line of best fit through the data set. Alternatively, for data which is not necessarily linearly correlated, and you might want to classify data, an alternative statistical model is known as K-nearest neighbors, or KNN, which is what we're learning about today. To understand how KNN works, let's look at the context of a literal neighborhood where we're trying to identify the sports identity of an unknown person in the neighborhood. If we select k equals 3 for our analysis, that means we are looking at the 3 nearest neighbors of that person in the center. So if we look at these 3 nearest neighbors, we identify that there are 2 Cubs fans and only 1 White Sox fan. And from this analysis, we would conclude that the unknown person is most likely a Cubs fan. Now, you as the scientist have control over the data in that you get to select k for your analysis. And there is no single right answer, but there are some guiding principles for how one might select k to get the best output from their data set. These guiding principles start with the fact that k should be less than the total number of data points in your data set. So for a small data set of 11 data points, k equals 11 would be considered too large a k value. Alternatively, for a massive data set of 100 data points, again, k equals 100 would probably be too large a k value to select. And this is because these large k values would instead be representing the majority classification of data rather than nearest neighbor analysis. Second, when selecting k, you want to select a k value that is odd. If we look at the example on the left using k equals 3, we see that the 3 nearest neighbors, we have 2 blue circles in class B and 1 red triangle in class A, and therefore the model is effectively able to predict class B for that unknown data point. If we instead look at the model on the right where k equals 2 is selected, the model is unable to predict an output because of the tie that results from 1 data point being in each class. The third consideration when selecting a k value is that k should be small with respect to the size of your data set. So in the cases shown, we have 11 data points. Therefore, for the analysis on the left using k equals 3, this is a small k value with respect to the size of the data set, and the model is effectively able to predict class B for that unknown data point. If we instead look on the right where k equals 7, we now see that k equals 7 for this small data set is likely too large a k value, especially considering that it is now including over half the data points in the data set. It is important to remember that this is all relative to the size of the data set. So here where we have 100 data points, a k equals 11 might be an acceptable small value for k because 11 is small with respect to the size of a 100 data point data set. And this model would successfully be able to predict class B for that unknown data point. So in summary, the guiding principles for selecting k starts with selecting a k that is less than the total number of data points in the data set. Second, your k value should be odd to prevent resulting in a tie. And third, your k value should be small with respect to the size of your data set. Best of luck using KNN analysis.